Hello. This is our last two topics of the semester. We need to talk about average value and we need to talk about consumer and producer surplus, which I always want to call surplus value, but I don't think that's the actual word that anybody uses. Here's the idea of an average value. Suppose f of x is a function on some interval. And suppose I pick a random point in that interval to plug into the function. A question I want to ask myself is, how big is the f of that point going to be on average? Or another way of phrasing it is, suppose I pick a million points, a million billion points at random in that interval, plug them all into the function, average those. How big will that average be? Picking a million points, like this is what you're thinking about when you say pick one and say how big do you expect it to be, is if you repeated the experiment over and over. So the thing you think about when you end up doing this is, I got some points, I'm going to pick a million billion points. In the long run, those points will be about evenly spread out. Like the proportion of the points that are in the left half will be about half in the long run, and the proportion in this 1/4 will be 1/4 of the points, and so on. So when I think about averaging these points, what I'm basically going to end up doing is adding up all these points, taking all of these values, and multiplying them by 1 over n, where n is the number of points. But that's the same as taking that value and multiplying it by the length of the interval, b minus a, divided by n, is about the width of the interval that that point should represent. As long as I divide it by b minus a also. And b minus a over n is the width of the interval, turns this magically into a Riemann sum. I'm taking all these points and multiplying by the width of their interval, except that I divided by the length of the total interval. Those points over here that were representing half of the interval, if instead of thinking of a point and saying it represents half of the interval, I can say if it represents half of the interval would be b minus a over 2, half of the points would be 1 over 2. Those are the same number, except they're off by a scalar of b minus a. I'm explaining this poorly. The point we're getting to is that the average value turns out to be basically the same as the interval. Take the integral of the function and divide it by b minus a. When you integrate a function, so what does it mean to average a bunch of numbers? You add up all the numbers and then divide by how many numbers there were. This is kind of the same idea. When I take an integral from a to b of a function, I'm kind of adding up all of those values. But then to divide by how many points there were infinitely many points, and dividing by infinity won't make sense. Instead of dividing by how many points, the thing we're dividing by is kind of how much points. We're taking that b minus a and spreading it out. There's a really good visual estimation of this. The integral from b minus a to f of x. So if the average is the integral from a to b, f of x dx, divided by b minus a, then the average value times b minus a is going to be the integral of the function. Well, this is the width of a rectangle. If I multiply that by the height of a rectangle, looks like our a value will be about here. this area of a rectangle should be this area of a curve. If this is my average value, which it looks like I picked it a little bit low, let me scoot that up a little bit, is the height so that the area of this rectangle equals the total area of the curve. If I think about taking the curve and moving the high parts over to fill in the low parts, like if I visualize this as like a can of Play-Doh or something that I'm trying to smooth out and make it all flat, the average value is the height that it is after you flatten it all out. Which, if you've thought about averaging numbers before and like cutting a little bit off the big one to move it to the little one until they're all about even, makes sense with the kind of thing you're doing with an average. So there's a couple aspects of this. One, you should be able to compute an average value. Example, if the value of my house is approximated by 150,000 e to the negative 0.01 t, where t is in years since 2000, say. What's the average value of my house over the last 5 years? The things I want to understand are, what is the interval that I'm trying to average that function over? The last 5 years, I'll take that as meaning from 2015 to 2020. That corresponds with t equals 15 to t equals 20. I want to know what's the average from t equals 15 to 20. That's going to be 1 over 20 minus 15 divided by the length of the interval, the integral from 15 to 20. So this is 1/5 of the integral from 15 to 20 of 150,000 e to the negative 0.01 t. This is a function we can integrate by hand. Most of the homework, so this section is from chapter 5. The book puts this section before you know how to do a definite integral by hand. So the book is going to be giving you functions that they expect you to just use your calculator to get the integral of. Be aware that the exam is going to once in a while ask you to do one of these by hand, and it's not, this isn't anything complicated. It's just asking you to use the tools that you got in chapter 6 to do this one idea from chapter 5. This is an integral we could do by hand, but I'm going to just use my calculator here. I need to change my window. Quit window. I need to be able to go out as far as 20. Let's graph it from 0 to 20, maybe 21. If I'd like to see some of the function, I need to be able to go up as high as 150,000. Let's try my function. Being able to see the function doesn't matter for computing the integrals, but I might as well. Hey, there's the value of my house. It's going down, crud. I want to calculate the integral of that function from 15 to 20. I'm going to copy that. So this is 1/5 of this number, 629,658,35. And I can do that. I divide that by 5. I get 1, 2, 5, 9, 3, 0, no, 1. 0.33, so 6, 7. There's the average value of my house over the last 5 years, is 125,931. There's not really much deep going on here. We're computing an integral and then scaling it by a constant. The constant depends on the integral. The interesting things going on are, like, my favorite thing about average value is it's such an easier concept to explain than a definite integral. You look at a definite integral with a Riemann sum and you take all those numbers and You have to multiply them all by these little values and add them up, and that's kind of weird. An average value, which is almost the same complexity of an integral, just amounts to pick a million numbers, pick them at random or uniformly distributed, or spread them out however you like, but plug them all into the function and average them. The word average has built in adding them up and multiplying by a little constant, and it sort of does all the work for you. I can imagine a textbook that treats the average value as the basic concept, and then the integral as the variant on that, just because this is so much easier to try to understand. So here's an example where we compute the average value. The cool thing about average value, another cool thing about average values, graph. Let me grab some graph paper. Is that they are the way. The book doesn't emphasize this much, and there aren't as many homework problems about this as I'd like there to be. So you can expect it to be hit harder in the exam than it was in the homework, because I love this concept. If I draw a function, let's make this 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and let's make you 10, 20, 30, 40. And let me just draw a simple, whoa, here's a function. And I want to ask a question. What's the average value of this function? Let's go from 30 to 50. Let's make it 25. Let's go from 15 to 50. I guess the way they'll say it is, what's the average value of this function on the interval from 15 to 50? So a thing we can do is, we've estimated integrals from graphs before. It's where the thing where you count how many boxes and you count some half boxes, and it's a pretty clumsy estimate. And it comes down to us counting stuff. We rely on counting because humans are really bad at estimating area. Even if you get pretty good and do a lot of practice, like standing on a ladder and saying estimate the area of the Walmart parking lot is something that humans are not very accurate at. There are things we are good at, that's not one of them. You hear, I've heard that there are sea turtles who will bury their 100 eggs, and if they come back and you move the eggs around, they don't care. But if they come back and you move the eggs around and remove one of the eggs, they know there's a predator nearby and they'll leave, because their brains are capable of looking at hundreds of eggs and counting them really fast in their heads. That's a thing that they've evolved to be good at. Estimating area is not something that humans have evolved to be good at. About how much area is this? I do not know. I could probably teach myself and get decent at it, but I'm not good at it as is. Here's a thing that humans are good at, though. If I try and estimate the average value, I want to ask myself, is this horizontal line the average value? If this is the average value, then the quantity by which we're too high will exactly cancel the quantity that's too low, right? This area will exactly cancel this area. I'm trying to visualize chopping off stuff from the top and moving it into the bottom until everything's even. That's averaging it out. And I am good enough to look at this and say, hey, no, this is smaller. And this is bigger. I can definitely see with my eyeballs, without counting squares or anything, that this shape is smaller area than that shape. That means that the stuff below is too big and I should move the line down, right? I can say that the average is definitely less than, what did I put it here? That's 15? 15 is definitely higher than the average. So let's try scooting it down a little bit. Let's scoot it down to 14. Now I'm imagining this shape. And this shape. Are these the same size? These might be the same size. This one's kind of... If I shade that in, does that look a little better? Maybe it's 14. Let's try again. If I scoot it down a little bit, can I tell it, does 13 look like a reasonable answer? Or will 13 look like it's definitely too low? Here's 13. Oh, this looks like it's definitely too low. If I visualize this shape, and I visualize this shape, this triangle thing is definitely bigger, right? I got all this stuff. And I got all, like, this the thing's just too skinny. They're the same width, but this guy's way taller and this guy's way skinnier. So the one on the right is definitely bigger. My average is definitely 13, between 13 and 15. So no counting necessary. I can say the average value is about 14. And I can say it's definitely between 13 and 15. I have a pretty good estimate, and beyond an estimate, I have an upper estimate and a lower estimate. I feel like it's definitely between here and here. Well, the average value connects you to the integral. If I wanted to estimate the integral, I could use this average value idea to get a decent estimate. Remember, the average value is the integral from 15 to 50 divided by 50 minus 15. What's 50 minus 15? It's 35. So this number is about 14 and definitely between 13 and 15. If I multiply this by 35, I can conclude that the integral from 15 to 50 is about 14 times 35, whatever that is. Can I do that? Oh, I can. It's 490, I think. And is definitely between... Let's pull out a calculator. What's 14 times 35? Yes. What is 13 times 35? What is 15 times 35? It's definitely between 455 and 525. This becomes a way to estimate an integral without counting boxes. And it's harnessing, we don't have brains that are evolved to be good at estimating area, but we do have brains that are good at estimating this is bigger than that. We have brains that are good at double checking that things are fair. Like, this is my favorite part. It's not that we planted our eggs in the ground that made us good at this. It's that we evolved to live in societies with a notion of fairness, and like our caveman ancestors were good at saying, hey, your piece is bigger than mine. We should try and divide this up fairly. This is a thing that you evolve with in when you have to live with other people. So that's the idea of average value. Most of the homework problems are going to tell you to... let me do one that doesn't have that. Let's estimate or find the average value of f of x equals x cubed minus 2x squared on the interval 1 to 3. And let's do this one by hand. The book will never specifically tell you to do it by hand because they put chapter 5 before chapter 6. I'm going to put problems like this on the exam just because it lets me ask you about 2 ideas in one question. It's good exam design. It's 1 over 3 minus 1, the integral from 1 to 3 of this function. How do I compute that integral by hand? This is a definite integral. If you haven't seen the lecture on chapter 6 yet, go watch that to understand what I'm doing here. But we find an antiderivative of this. 1/4 x to the 4th minus 2/3 x cubed. And now we need to evaluate that from 1 to 3. So this is 1/2 of plug in 3. 1/4 3 to the 4th minus 2/3 3 cubed minus plug in 1. Plug in 1, you get 1/4 minus 2/3. This is half of, I guess we want a common denominator, 81 over 4. 27 times 2 is 54 over 3. This reduces, but I'm going to want the common denominator anyway, because this one's in thirds. Common denominator is 12. 81 times 3 is 243. Minus 54 times 4 is 216. Minus 3 plus 8 over 12. What is 243 minus 216? That's 27. Minus 3 is 24. Plus 8 is 32. I get half of 32 over 12. 32 over 12 reduces by 4. That's 8 over 3 times a half. This is 4/3. Oh, that's a simple number. The average value of this function on this interval is 4/3. If I plug in a million numbers from 1 to 3, plug them all into this function, they will on average be about as big as 4/3. That's average value. Compute an integral divide. Or, more interestingly, look at the picture to estimate the average value and use that to estimate the integral. These estimates you get tend to be way more accurate. Like this estimate of 490, this isn't a function I can plug into a calculator and check what the actual value is, because I just drew it. But in general, doing this average value thing tends to give you more accurate answers than the box counting thing. So, I mean, that's a pretty cool skill to have, being able to view these things in this direction. Okay, that's average value. That's the last topic in Chapter 5. Let's talk about surplus value, which is the last topic in Chapter 6. This is stuff that I skipped in the spring that I don't have to skip now. And these are both tend to be easier topics than the other stuff in Chapter 6, so I think putting this on the exam is a net benefit, although it is more homework to get through. So surplus value is a concept from supply and demand. I don't know if you've had an economics course yet. I don't know if they talk about this in high school classes, but there's this fundamental idea you should be aware of about supply and demand. There's two curves, a supply curve and a demand curve. Do we write this as a function of P or as Q? We will typically write this with Q on the x-axis and price on the y-axis, although you can do them either way. I feel like in economics classes you usually put them the other way around, but all the demand curves we've been talking about were as functions of quantity rather than as of price. I guess we talked about this some when we did when we were computing revenue from price and quantity. Revenue is price times quantity. Price might be the function or quantity might be the function. You could have it either way. For now, we're treating price as the function of quantity, which to me is the less intuitive, but it makes the better picture here. So the idea of these curves, the supply curve, I'll call that S of Q, S for supply, is the amount, the price at which the supplier is willing to make and sell that quantity. And it's an increasing function. If the price is this low, they're only willing to make 100. If the price gets higher, they're willing to make more. You want them to be willing to make this much, then the market needs to be able to offer them that price. The higher the price for a thing is, the more willing a company should tend to be to make and sell more and more of that product. Like, this is their concept, is at a good price, we can do more business. The demand curve is the same thing from the consumer side. The demand curve is the price at which the public, or the market, let's call it the consumer base, is willing to buy that many. And it's the same thing in reverse. If you want the public to buy 300, well, they're only willing to pay this much for 300. If you want them to buy more, you need to make the price go lower. And the low-level thing you probably saw on this in your economics class is there's an equilibrium point. The place where these things is what we call the fair market value. This is the fair market price. Or I guess they call it the equilibrium price. And this is the equilibrium quantity. And in a market with competition and all other things being equal, this is how the prices of most goods end up being set. If the price was lower, the consumers wouldn't be as willing to make as many. And if the price was any higher, the public wouldn't be willing to buy that many. So this is the price at which the stores empty their shelves at the same rate that people are buying them, you know. And when things get out of whack, if there's a drought or if there's a surplus or whatever, the price usually moves around to account for that. So here's the cool idea that causes us to have this section. Here's a question. So I want to pick a specific product. I'm gonna pick frozen pizza because I like frozen pizzas. I've been eating a lot of frozen pizza staying in these days. If this is a price of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I guess I'm not going to try and worry about it. Let's just make this $5 and $10. This is some brand of frozen pizza that sells for $5. The fact that this point is this high, the fact that, let's call this, we have a name for this. I guess we call this P of Q. Let's call it D of Q for demand. The fact that D of 100 is 9.5 is saying that at a price of 9.5, the public is willing to buy 100 frozen pizzas. And at a price of 101, or at a demand supply of 101, it's a little bit less than 9.5, whatever it is. That means every time you step over by one, there is a person who is willing to pay this price for it, who is not willing to pay that price for it, right? When we went up to 101, the function is decreasing. The reason it decreases is that the lower the price, the fewer people are willing to buy. And in particular, there is some specific person, they probably don't know who they are, who would have bought the pizza for this price and wouldn't have bought the pizza for that price. Consumers don't actually have to make these computations in their head. I don't walk down the freezer aisle saying, I am willing to buy at this price I will buy 2 pizzas, and at this price I will buy 3 pizzas, and at this price I will buy 4 pizzas. Although, inherently, the lower the price is, I will buy more. If there's a sale, I will go nuts. So those numbers do exist somewhere in my head. Not that I have worked them out, but they exist in the abstract. Okay, here's the radical concept. What is the value of a product to a consumer? What is the value? What is its value to a producer? And the radical answer that feels obvious until you think about what the consequences are, they are bigger than it seems like it would be. The value of a product to a consumer is the highest price they would have paid for it. I'm a person who really loves frozen pizza. I think it's a great value. I might be this person who was willing to way overpay for a frozen pizza. If I was willing to pay $9.50 for it, then its value to me was $9.50. Like, that hypothetical thought experiment proves it was worth at least that much to me, and it wasn't worth more than that to me because I wouldn't have paid this much. So, like, this is a number that this graph can specifically work out. What is its value to a producer? Its value to a producer is the lowest price they would have sold it for. Which is also a value we can see on that graph. That first frozen pizza I'm thinking about buying, the one I would have paid $9.50 for, I can see they would have sold it for 80 cents. Is that, yeah, we measured these in dollars. This particular pizza, the one that transitions from 100 to 101, they would have been willing to make and sell that pizza for as low as 80 cents. So that's the value it had to the pizza company. To the pizza company, it was worth 80 cents. To me, it's worth $9.50. The concept of surplus value is this exchange. When I buy that frozen pizza, they are selling something that is worth 80 cents, and I am buying something that is worth $9.50. Okay, if we had like a bartering, haggling system and I had to negotiate my price with Palermo's every time I buy a frozen pizza, it's Palermo's. They make the best frozen pizzas. They have these thin crusts. They got this spicy sauce. It's really good. I don't have to negotiate with Palermo's. I have the backup of the market behind me that is telling that is setting the market price at this equilibrium value. Like, I don't have to convince them to not charge me $9 when they would have been willing to sell it for 80 cents. They don't have to try and beg me to pay more than 90 cents when I would have been willing to pay $9. All these other people being willing to buy and sell at these prices set the price at this middle amount, $5. So I'm paying $5 for something I get this is the magical thing about trade. Trade increases the value of stuff in the world. Before the transaction, they had a pizza that was worth 80 cents. After the transaction, I have a pizza that is worth $9.50. Prior to the transaction, I had $5. After the transaction, they have $5. The $5 that we're trading doesn't change its value. That feels like a meaningless statement, but it's sort of the definition of what money is the money doesn't change its value as it moves back and forth. But the things we buy and sell do change value because they are worth different amounts to different people. This thing that was worth 80 cents before the trade is worth $9.50 after the trade. And this is the magical property of trade, is it increases the value of stuff in the world. And the thing about the equilibrium price... Okay, so that's the surplus value for one person. This part is called consumer surplus, because it's the value that I got. This area of this rectangle is the width 1, height 5 minus 9.5 is 450 is the value I'm getting from the trade. This rectangle is the producer surplus on that one pizza. Width 1, height 5 minus 80 is $4.20 is their value gain out of the trade. So I'm getting $4.50 of value from the transaction. They're getting $4.20 of value out of the transaction. It's tempting to think about this as a concept of profit. Like, it feels close to profit. I'm trading $5 for something that is worth $9.50, so I profited $4.50. The thing is, that's not what profit means. Profit is money to money. This is only measuring value. I'm trading $5 for something that is worth more than $5, but I can't turn it back into $5. Like, I'm not selling the turnips afterward. There's no way to use the word profit. Like, we want to keep this as a separate concept. The thing where an integral turns into this is if we ask the same question about what is the total surplus. So, if instead of asking what is the value what is the value I gain from buying that one pizza, if I ask what is the value gained from all consumers from buying all those pizzas, that's going to be this total area. This area is the total consumer surplus at equilibrium price. And this area is the total producer surplus. At equilibrium price. Okay, let's do a specific example that gets to this. Oh, the total of these is called total surplus. All right, let's do an example. We've gone too long without actually doing a function. For some product, the supply function is S of Q is 0.5 Q squared, and I want to keep in mind that this is a price, the price at which they are willing to sell that many. And the demand function is D of Q is, I'm going to call that 800 minus 0.2 Q squared. This is also a price. We don't want to use the letter P for them because then they would have the same letter. So I'm giving them supply and demand names, but they're both representing a price at which they're willing to sell, a price at which someone is willing to buy. Let's find the equilibrium price and quantity. And 2, let's find the consumer surplus, producer surplus, total surplus. The total surplus is just add up the first two. It's not a separate thing to work out, really, although we can. Let's solve this. How do I find the equilibrium price and quantity? Well, the equilibrium price and quantity, I don't need to know too much about these graphs to know one's increasing, one's decreasing. The place where that they intersect is the equilibrium quantity and price. How do I find the place where two curves intersect? I set those two functions equal to each other. I set 0.5 Q squared equals 800 minus 0.2 Q squared. And I want to solve this. I guess I'll add 0.2 Q squared to both sides. I get 800 equals 0.7 Q squared. Divide both sides by 0.7. I get Q squared is, what's 800 over 0.7? It's like 1100? $1142.85. I guess that rounded up to 86. Q is going to be plus or minus the square root of 1142.86. We immediately throw away the negative square root, but I'm putting it there out of habit because that's a power of 1/2. That's 3381. I'm getting 33.8 is the Q value. To find the equilibrium price, there's a temptation to round this to the nearest integer, and that will often make sense. I'm going to try and keep the digits here because there's a chance that Q is being measured in thousands. If Q is being measured in thousands of frozen pizzas, then I shouldn't round until the next, 3 digits later, so... you can't sell 33.8 frozen pizzas, but you can sell 33,800 something in the teens frozen pizzas. Maybe that's what's going on. I'm just going to leave the digits there. What's the price that goes with it? Well, that's the y value that I will get from plugging 33.81 into either of those functions. I should be getting the same thing. If I take 0.5 times 33.81 squared, I get this. If I plug it into the other function, 800 minus 0.2 times 33.81 squared, I get almost the same thing. I'm off by 20 cents. Our equilibrium price is 571 something. I'll just call it 571. Okay, with these, I'm now basically able to set up the integrals that I need to know. I want to know if I want, so, wait, what's the question they're asking? Equilibrium price. Actually, you know what I should be doing? I shouldn't be plugging 33.81 into these. I should be plugging in all the digits. 0.5 times... I'll just type in a bunch of digits. I really want to be using the answer key to type in all the digits, even the ones I can't see. But let's not let our rounding mess up this part. 806.17.019 squared. Our more accurate answer is 571.43. The equilibrium quantity is 33.81. Cool. How do I find my surplus? I drew them as pictures. I didn't compute them at the time, but I can set up that integral. This equilibrium price, this is the line y equals, or p equals, 571.43. This value we worked was 33.81. If I want to find this area, the consumer surplus, is the integral from left to right of top function minus bottom function. That's going to be the integral from, we go left to 0, right to 33.8. Our top function is the demand curve is 800 minus 0.2 squared minus our bottom function is just the number 571.43. And I stick that into my calculator, and that is the consumer surplus. I'll skip that part because you've watched me calculate some integrals enough already. The producer surplus is going to be this area is again the integral from left to right of top minus bottom. The left is still 0, the right is 33.81. Our top function is now the line 1 is 571.43 minus our bottom function is now this is the supply curve, is 0.5 q squared. This should be dq to make sense, although when I stick it in my calculator it'll be the x. I guess I might as well do these. Let me graph the function that I want to integrate. I just graph that. 800 minus 0.2 q squared minus 575.43. I need a window that goes out past 33.8. I'll do that from 0 to 40. It looks like 1,000. It's high enough to see the whole thing. Now, calculate the integral of that function from 0 to 33.8. $5,016.17. It's worth pointing out this is, again, an integral we could do by hand, but this is an applied problem. This is a good place to say, hey, just pull out your calculator. Oh, wait, did I do the wrong one? That was this one, it's 5016. I put the answer in the wrong place. To get the producer surplus, I need to integrate over the same region, but I need a different function. Where's my mouse? There it is. Now our function is clear 571.43 minus 0.5x squared. Again, it should be hitting 0 at that point. Calculate the integral from 0 to 33.81. We got 12,878.59. Cool. Producer surplus is this, consumer surplus is that. There we go. The questions get more interesting when they talk about what happens at an artificially high or low price. So the market equilibrium says it should be here. What happens if the price is higher for some reason? Why would the price be higher? The standard textbook example is if the producers collude, like normally there's a free market, and the reason everyone is stuck at this price is because if I charge higher, someone else will charge less, and they will steal all the business. What happens if all of the producers agree at the same time? Like, what happens if all the airlines agree, hey, we're going to start charging $50 to put for luggage, and if we all do it, then they just have to pay it, and, you know, we'll get the money. Instead of them competing with each other, what happens if they collude beforehand to price fix? This is illegal. The weird thing is it's illegal for them to meet and say this is what the prices will be. It's not illegal for the one company to say, you know what, I'm going to jerk it up. Why don't you do the same thing? We'll just see what you do. And then they all do it, and like that version where it's like a double bluff thing is legal. What happens if the price is artificially high? So now the price is something above equilibrium. We got these two quantities. This is how much people would be. This is how much they would be willing to sell at this price. But that's sort of irrelevant because they can't sell that many because the people are only willing to pay this much for that price. So the thing that happens is whichever curve you intersect with first, that's the one that actually happens. We can still ask about consumer surplus. We can still ask about producer surplus. But they are these new values. What happens when they jack up the price? The consumer surplus is definitely lower than it would have been. The consumer surplus would have also included all this extra area. So the consumers are getting less value out of the trade. What happens to the producer surplus? Well, it used to be all of this area. They've lost some, and they've gained some. So they've lost, they would have had this area, and they're trading it out for this area. Is that a good deal for them? It depends on the shapes of the curves involved. In this one, it looks like the producers are definitely getting more surplus out of it. They are happy to be jacking up the prices. The consumers are sad to be jerking up the prices. This is the concept of why it's illegal. Like, capitalism doesn't work without free markets, and we just don't have free markets when this happens. What happens if the price is set artificially low? Okay, so we can do an example of computing these integrals, but you just find the new price. You do the same integral left to right of top minus bottom function. The bottom function is this new price. The right is this new quantity, which are different. The picture basically shows you everything you need to know, though. What happens if you have an artificially low price? Why would a price be artificially low? Prices get lower when there's too much of a thing. Oh, so the other reason for an artificially high price is if there's like a drought or something and they aren't able to make as much product, so the quantity gets pushed over here, which is the new price and the new whatever. I don't know if that's artificially high, like if nature is pushing. I don't know what the word artificial means in this sense, but it's different than the market would have sustained. What happens if your price is artificially low? I don't have many good examples of a thing with an artificially low price. I guess sometimes there are laws that you can't charge more than X for something. Maybe hand sanitizer is got an artificially low price because the people who've been hoarding it would like to be selling it for profit, but they're not being prevented from that. Same deal. The quantity you care about, like this would have hit the curve twice, but this one doesn't matter. The fact that consumers would have been willing to buy a whole ton of this stuff at this artificially low price doesn't matter because the producers aren't going to make that much. They're not willing to make more than this much at this price. So you have this is your consumer surplus, and this is your consumer surplus. That one's the consumer one, that one's the producer one. Same deal as before. And yeah, that's you work out the same thing. Integral from left to right of top minus bottom. Your new right value has changed. Your top/bottom has changed depending on which thing you're working out. This time the consumers might be getting more surplus value. The producers are definitely getting less surplus value. What's an example of a product with an artificially low price? I guess there's that hand sanitizer one where people are being prevented from gouging the public. I guess sometimes groceries get subsidies to keep the prices low. The big example I always have in my head of this is organs. If you need a kidney transplant, you're not allowed to pay a person to give you a kidney. You are allowed to pay their medical expenses, but that is it. This is like a thing that happens. If you're giving a kidney to a family member, there's a good chance that the hospital won't want to interview you and confirm that your family member is not paying you for it. Even if they are letting you, like, hey, you're not going to be able to work, stay at my place, don't tell that to the hospital. They won't let you give the kidney if they perceive it as a transaction happening. Like, anyway. That's a thing with an artificially low price of 0. Even though there would be a great market for kidney transactions, I guess the decision's been made that we don't want to live in a society where we're asking homeless people to sell their kidneys. Like, even though presumably they would be happy with the transaction, and the people who need the kidneys would definitely love to have more kidneys available. And I'm not saying that's good. It's great to not live in a society where that's ghoulish. That's horrible. I'm going to stop talking here. That's consumer and producer surplus. Cool. I'll be back. I'll be posting a practice exam later today. I'll be going over that practice exam tomorrow. And I'll see you around and end stream.